So let's now apply the numerical methods to one of the interesting problems. If you have simultaneous algebraic equations or in XYZ, then how do you apply? Okay, so we'll see that if you have simultaneous algebraic equations, linear algebraic equations, then we'll see one of the method which is quite popular, the Gauss-Seidel method, which is there in the syllabus as well. So we'll see Gauss-Seidel iteration method. Okay. Okay, so for this, first let us the Gauss elimination. Remember, you would have heard about Gauss elimination, which is a direct method. I mean, given three equations and three unknowns, you can easily solve. So that I'm not going through it. I'm just going through the iterative procedure of solving simultaneous linear equations. Okay, because sometimes the direct method will always give you exact solutions, but uh, it may not work. I mean, most of the time, sometimes it will be difficult to solve using the direct method. So then we apply an iterative method in which we basically start from an approximation to the true solution and then obtain better and better approximation over the computation cycle, which is repeated as often as you need the desired accuracy. So let me describe this method. So consider the equations a1x plus b1y plus c1z is equal to d1, a2x plus b2y plus c2z is equal to d2, and a3x plus b3y plus c3z is equal to d3. So now I can just rearrange this, the first equation. I can just divide by a1, so I'll get the terms. I'm just writing like this, that is d1 by a1 is k1, and then b1 by a1 is l1, and c1 by a1 is m1. So that's what I'm writing, xyz. So similarly y also, the second equation I can rearrange in this form. Okay, so these are nothing but each of these equations are just rearranged to give this form. Now what does this method says is that we start with an initial approximation. We start, so let me call this as 1, this as 2, and this as 3. So we start with initial approximation y naught 0 and z naught 0, and get a value of x1. So x1 will be basically k1 from the first equation. From first equation, x1 is k1. Okay, now we use second equation and substitute x1 is equal to k1, whereas z is equal to z0. So we substitute x is equal to x1, which is k1, and z is equal to z0, the second equation. So we get y1. So basically y1 will be basically your k2 minus L2 x1 plus m2 minus m2 z0. So this is how we get an approximate. Now we use a third equation and we substitute x is equal to x1, y is equal to y1 to get z. So we get z1, which is k3 minus l3 x2. This is x1, and this is also x1 minus m3 y1. So you'll get z1. So now, and so on. So as soon as new approximation for the unknown is found, it is immediately used in the next step. So this is the iteration. So now this process of iteration is continued until we get the desired accuracy. So this is quite simple method. As soon as you get a new approximation for an unknown, it is immediately used in the next step. Okay, so that is how it is different with the Jacobi method, because Jacobi method we use the same approximation. We initially use x0, y0, z1. We define it to be 0 0 0. We solve for x1, y1, z1 simultaneously, and then used these in the next step. But here that's the difference. In the Gauss-Seidel, immediately we know the approximation, it is immediately used on this. So this was the difference with the Jacobi method. Let's solve one problem describing this Gauss-Seidel iteration. So solve by Gauss-Seidel method. Okay, so solve by Gauss-Seidel method, and the equations are 20x plus y minus 2z is equal to 17, 3x plus 20y minus z is equal to minus 18, then 2x minus 3y plus 20z is equal to 25. So these three equations you have to solve using the Gauss-Seidel. Okay, so let me just rewrite these equations uh, in terms of x, y, z. So I can write the first equation being 17 minus y minus 2z plus 2z. Okay, so this is the first equation. Okay, let me call this as 1. Second equation is 1 by 20 minus 18 minus 3x plus z, and z is equal to 25 by 20. I mean z is equal to 25 by 20. Sorry about this, 1 by 20. Okay, 25 minus 2x plus 3y. So let me call this as 2 and this as 3. So we have three equations to solve for. So we initially start with, so take equation 1 and substitute y naught is 0 and z naught is 0. So then we get x as 1 by 20 into 17, which is basically 0.85. Okay, and now we got, so now take equation 2. Okay, so x is basically x1, which is 0.85 now, and y is basically, I mean, we need to find y, so z is basically z0, which is 0. So this we have to substitute in equation 2. So we'll get y as 1 by 20 minus 18, x is 3 into 0.85 plus z, which is 0. So this gives rise to minus 1.0275 as y1. Okay, so now take equation 3. So immediately once you got x, you are just using it in the next step. So that's the immediate usage of the approximated. So take equation 3, x is x1 and y is y1. Okay, in the last of the equation, which is third equation, so z1 you will get 1 by 20 and then 25 minus 2 into 0.85 plus 3 into minus 1.0275. So this will be 1.0109. 1.0109. Now let's use the second iteration. So this was first iteration. Let's do the second iteration. So similarly, x2 will be 1 by 20 now, 17 minus y1 plus 2z1, which if I calculate I get 1.0025. So this is just, I mean, once you got first iteration, you started with y naught z naught, founded out x1, then you used x1 and z naught in the second equation, got y1. Similarly, now in the third equation, you know x1 and y1, the newly approximated values, we got z1. Now for the second iteration, when you take equation 1 again, so this is iteration 1. So now for the second iteration also, you have to take equation 1 and then substitute. Okay, so we'll get x2. Similarly, y2 will be basically your 1 by 20 minus 18 minus 3x1 x2 now plus z1, because z is the latest updated value is z1. So this will be minus 0.99939 and 8. So this and all you have to check with the calculator. Now using the third equation, z2 is 25 minus 2x2 plus 3y2. So this value comes out to be 0.9998. So this is second iteration. So now third iteration, so we have to repeat until the values get almost equal. There's no change, almost equal to the second or the third order of. So third equation also, when I take equation 1, now I have to substitute y2 and z2. So this will be, which is 1. Now in the second equation I have to substitute now x3 and z2. And this is minus 0.1, and z3 is 1 by 20. I have to substitute x3 and y3. This is 1.0. So now if you compare the second iteration values and the third iteration values, they are practically the same. Okay, so we can stop at this point and we can say that the solution is x equal to 1, y is equal to minus 1, and z is equal to 1. This is the solution of the simultaneous equation. So this, in fact, you can solve it by direct method, but just to explain the idea behind the iterative method, this is how it works. So what we observe here is that since the most recent approximation of the unknowns are used while proceeding to the next step, the convergence is faster in this method when compared to the Jacobi method. I have already explained you what is Jacobi method. Jacobi method, the most recent value is not used. In one iteration, you use only one set of values, x0, y0, z0, and then in the second iteration, you use x1, y1, z1, which are calculated at the end of step 1. So convergence is faster in Gauss-Seidel method. And another observation in the Gauss-Seidel method is that the Gauss-Seidel method converges if in each equation the absolute value of the largest coefficient is greater than sum of the absolute values of the remaining coefficient. So that is again observation on step on terms in terms of the coefficient. So this was all about Gauss-Seidel method. And okay, so there are other combinations. I mean, the Gauss elimination method is there, but that is a direct method. And direct, I mean, so basically in this solving linear simultaneous, these are all linear simultaneous equations, remember. So direct methods, we have the Gauss elimination method and the Gauss Jordan method, which are just the way you know how to solve. I mean, you have to just eliminate either x from two equations, get the equation two equations in y and z, and then two equations. So basically three unknowns, three equations you should be able to solve. Now even this equation what we have solved right now, you can solve it by Gauss elimination, but we have just applied the iterative method, which is Gauss-Seidel method. So in iterative methods you have two known methods, which are Jordan which are Jacobi method and the Gauss-Seidel method. The Gauss-Seidel method is quite popular, so I have just explained you Gauss-Seidel method, and we have solved one problem explaining the iterative process. So remember one thing, the recent approximation values are used for the next step. The immediate values are used for the next step. So overall in the numerical methods we have seen, apart from basic numerical methods for solving algebraic and transcendental equations, we have seen the bisection method and the false position method or the equivalent method and the Newton-Raphson method. Whereas in the numerical integration we have seen the trapezoidal rule, Simpson 1/3 rule, and 3/8 rule, and we have solved the relevant examples. And in the numerical solution to numerical methods applying to differential equations, we have solved all the methods. I mean, we have solved the Euler method and the Runge-Kutta fourth order method, which is popularly known as Runge method. And now here in this section we have just solved the solution. I mean, we have just solved how to apply iterative procedures to, or basically the numerical methods to solving simultaneous linear equations. So this was the idea. This was the idea. And so numerical methods, mostly it is used in solving differential equations. All your MATLAB has, uh, I mean, there is inbuilt functions which solves the ODEs. So all that in MATLAB it's already built, but rarely we use it for solving quadratic equation, because because nowadays even in the calculator you can solve non I mean the cubic or the fourth order equation. So that's the point. But differential equation, it's some initial portion has come in the calculator also, but mostly in MATLAB is quite famous at the MTech level, solving differential equation numerically. So I think if we solve one example in each, it should be okay. So that's it for the numerical.